Look at us. Look at us live. Wow. It's like YouTube knows what to do. Amazing. And I have excellent connection. Wow. Let me turn my phone off and then we're ready to rock. Now, I got an email notification for my own going live. It says, "You're now live." Yes.
Congratulations.
Thank you so much. All right, last time they said that y'all's voice was low. I think I know why. All right, when do you speak?
No.
No, okay, perfect. I should be better. Speak one more time.
I'm sorry, I can't do that.
Wow. Wow. So mean. All right, this is our.
I'm sorry, Dave. I can't do that.
I'm sorry. This is our second to last stream for this specific book. It's our book club, our sixth meeting. We're gonna go over, I believe, chapters 9 and 10, if I'm not mistaken, if I can count. The book is on the screen. It is a Designing Distributed Systems. It's a free book. I guess Microsoft made this free. Again, I'm only streaming it and sharing it because it's a freely available book. And then we're just gonna discuss the chapters. But hopefully YouTube doesn't yell at me for that, or other people. But it's fine. I can actually look at the chat this time. So if you have chat questions, I'm there. And let's get into it. Cool. I like to always do a brief recap of what we covered. So last week we did 7 and 8, I believe, if I'm not mistaken. We did scatter gather, and we did event driven processing and functions. Or I said that backwards, but the TLDR there, scatter gather, is you take a user's request, you split it up into multiple subcomponents that you can execute usually in parallel or concurrently. Once those concurrent executions finish, you gather all of the results back and you send the result back to the user. And then functions and event-driven processing. There are services out there now that are like functions as a service. AWS Lambda comes to mind. It's one of the most popular ones, where instead of like deploying your code to like a server, you can just write your function, deploy that to Amazon, and it'll take care of like running that function for you. And then there's event-driven processing, where instead of having like a long-running service, you can have more of an event-driven architecture where an event fires and it spawns some work to be done. And then that can fire events and so on and so forth. So pretty interesting stuff that we covered last week. But this week we're going to cover chapter 9 and chapter 10. And these are kind of small. I don't think we're going to take a lot of time on these, to be honest with you. But yeah, so chapter 9 is ownership election, and chapter 10 is like work queue systems. Chapter 10 actually goes into part 3 of the book, so we're moving out of part 2. Like this current club that we're on is the first chapter is in part 2 and the second chapter is in part 3. So we're kind of straddling 2 parts here. But let's talk about ownership election. Anyone have any questions, comments, or concerns about ownership election?
Yeah, it's real weird.
Yeah, it kind of is a weird topic.
Or it's just complicated, I guess. Like I haven't done a lot of what's the word? Like multi-threaded like application programming. Like I know about it.
Yeah.
So it's like I understand like the concept of like the locks and stuff that you need to like switch between them, but it's pretty weird, especially like for like in a distributed system.
Yeah, this is a fun one. Ownership election is an interesting one, and the author kind of self-admits that we're coming out, like we've learned how to scale up requests per second, how to scale the number, like the amount of data that we're serving, right, using like sharded and stuff. We also learned how to like lower the time to process a request using something like scatter gather or so on and so forth. But now we're going to talk about how we scale, how requests are like handled and assigned, and we cover ownership. And you're right, ownership's weird, right? It's a weird thing because most of the apps that most developers or engineers write don't really see this sort of multi-node execution where ownership becomes a thing. But the author says to us, like, when we're deploying our applications to a single server, ownership is very straightforward, right? You have a single instance of your app, so of course that single instance of the app has to own the requests and has to actually serve them and perform the work and do the things. So it makes sense, right? Like it's kind of difficult. It's kind of hard to imagine like a world where it's like, wait, I have a single node, but we need some ownership election. Like that doesn't make sense. But when you have that same application deployed across multiple servers or multiple nodes, how do you know which one's supposed to handle the request, right? You don't want to get into a situation like there's a few of us in the chat right now. And if somebody came up to us and asked us for, I don't know, a pencil, we don't all want to go out and get the pencil immediately because that would be a really poor use of our resources, right? So we elect a leader, we elect a representative, we elect an owner that will go get the pencil for whoever's asking for it, right? So if I say like, if we happen to decide like that I'm the leader this time, Matthew's the leader, you get the pencil. Then when people come to me asking for pencils, or they come to this group asking for pencils, I'll be the one handling that. And if I happen to be away or down or whatever, then one of you can take over being the leader for handling pencils or giving out pencils. Yeah, exactly. No, I'm the leader. Exactly. So ownership is important in a distributed system because you don't want requests to not get handled, right? You don't want it to like, obviously that would be really bad if requests don't get handled. But I think what's even worse is if requests get handled multiple times, right? Because that can leave your system in an undesired state. So we need to have a mechanism by which we can have these systems identify an owner or a leader, and those owners or leaders are the ones that are going to handle the logic or the requests that come into the system. And mind you, that doesn't mean there's not going to be other workers and stuff, but the requests flow through those owners, those leaders, so that they're processed correctly, right? And not duplicated and whatnot. The author gives us this nice little diagram here showing like a 3-node service. They do some sort of election protocol to determine who is going to be the master or the leader, whatever you want to call it, the owner. And that's highlighted in this like black box. So number 1 is currently the master. Requests come in, they get served by master 1, and it does all the thing. But if master 1 goes down, the remaining nodes or remaining masters will have to do another election and determine a new leader, a new master. They determined it to be master 3, and then the master 3 serves requests. And then if master 1 comes back in, it doesn't just gain its rights back. It lost it when it left the group, so now master 3 remains the leader until it maybe falls over. So this sort of ownership is important because at any given moment there should be a owner in your multi-node application. And the author admits this whole idea of ownership election or distributed ownership is probably the most complicated thing, and the most important thing when you have distributed systems. So much so that there's whole products built around it. Any questions so far about ownership? Cool.
Nope.
So the author goes into saying you might not even need this whole master ownership election thing. It might be advantageous to you to just keep your primary service that handles user requests as a single node, right? And then you take the hit if that single node were to die and you have to restart it or whatever. You take that hit in availability, because that might actually be a more available and less complex solution than introducing some sort of leadership election or ownership election into your system. And the author says, imagine if you had a single container in running under Kubernetes. If that container crashes, Kubernetes is going to start it. If the container hangs for a long time and it has a health check, it'll be restarted because the health check will fail. And if the node that's running the container dies, the container will just be rescheduled to another node. So you get a lot of cool benefits in availability just from your operational platform, right? Kubernetes. And the author says, since you have all these guarantees, you might not even want to make your single service multi-node. You might want to just keep it on a single node because these guarantees are good enough. You can get like 3 to 4 nines of uptime here just with these certain guarantees. And the author goes into like some of the details of the math behind getting 3 or 4 of those nines. But the point the author's trying to make in these couple paragraphs is you might not even need this at all, depending on what your service is, depending on what your goals are, blah, blah, blah. Any questions there? Cool. All right, so the author then starts to go on to describe like what is master election or ownership election, right? Some products out there call it leadership election, right? Whatever terms you hear, you might hear like those slightly different terms, but we're kind of talking about the same thing. And what it boils down to is that imagine you have a service named Foo, and I'm going to just use the author's example here because I think it's perfect. Imagine you have a service Foo that has 3 replicas, right? Foo 1, Foo 2, Foo 3. There's also one object in your system called bar that can only ever be owned or operated on one of the replicas at a time. The replica that owns or operates on this object is often what we call the master, right? Or the leader. And that's why we use these terms called like master election or leader election, because there needs to be some sort of protocol that determines how do we select this master or this leader so that it can own this bar object without conflict. Okay? The author says there are a few ways to implement this leadership election. You can use a consensus algorithm like Paxos or Raft. If these names are unfamiliar to you, I encourage you to just read up about them on Wikipedia or something. Just understand these terms. Raft is a very common one that we use like in the field. You'll see it used in the field. I know a bunch of HashiCorp products use this. I think, does Kubernetes use this? No, I don't remember. I think Kubernetes uses etcd straight up. I don't remember. Anyway, look up these words, see what they do, and you'll see that why they're useful. You also don't need to use something like a consensus algorithm. You can use a distributed key value store, and you can use that to implement what we call locking. That way, you can have people nodes in your system lock before they mutate a resource. Sorry if I'm out of it. I'm so tired. I barely got sleep last night because my dog was not feeling well and she was throwing up a lot. So I'm a little out of it. But yeah, so the author says there's 2 kind of ways to have this leadership election. You can use a protocol, right, like Paxos or Raft, or you can have a distributed key value store, and you can do a lock, right? So that way only the leader has the lock, right? And while the leader has the lock, it's the leader, right? Think of the lock way of you ever hear like a talking stick, or I have the mic in my hand, so I'm the only one that's allowed to speak, right? If you're in a group setting and there's one microphone, whoever has the mic is a speaker. That's kind of what the distributed lock is, right? Whoever holds the microphone is the one that's allowed to speak. Whoever has the lock is the one that's allowed to lead, right? So the author is going to talk about this locking mechanism rather than the algorithms like Pax or Paxos or Raft. So just keep that in mind. We're not going to cover the algorithms. Yeah.
The distributed key value store is just sort of a drop-in replacement for these consensus algorithms, because I haven't looked at them yet, but I'm assuming that it's basically just some sort of complicated mathematical operation to be okay, take data from all of these masters or servers, whatever.
Yeah, I wouldn't say it's a drop-in.
You combine it and say okay, this is what the actual state is of
right.
who owns
that data. Resources. Yeah.
Right, but the key value store is that is that like just a more strict version basically that you can
A,
easily do yourself?
a key value,
Or
the distributed key value store by itself isn't enough to be like like a leadership election thing. We're going to implement logic on top of that distributed key value store to make it a thing. So yeah,
it's just the background to like store the data that you need.
Correct.
To actually
Exactly.
choose who has control.
Exactly.
Okay.
Exactly. In some like really critical systems or whatever, maybe you'll look at Paxos or Raft. But again, using something like Paxos or Raft introduces a lot of complexity. Mm-hmm. So it's a trade-off you're gonna have to make. They give you some benefits, but there's complexity involved. Whereas this key value store, if you have a distributed key value store, you can just it's a lower complexity, right? But you'll see that like as we read through this, that lower complexity also means we have to be responsible for some of the edge cases.
Yeah. Okay.
Cool. The author says that there's an underlying concept that powers these locks, and it's called the compare and swap. And all the compare and swap does is it atomically writes a new value. I'm going to read this paragraph verbatim. Compare and swap atomically writes a new value if the existing value matches the expected value. So if you give me like a key and then you give me the existing value of that key, like so let's say the key is foo and the value is 7. If you say, hey, given key foo, if it's 7, set it to 8. That's what a compare and swap does. So compare it first and then swap it if the comparison holds true. If the value doesn't hold true, right? If the existing value that you've given me doesn't hold true, return false. And if the value doesn't exist at all, then and it's not, the current value that I expected is like not null, then it's an error case, right? But if the current value is null, then insert it. So this is just a fancy way to say like, hey, we can do like an update to a key value store as long as we know the previous value and the next value, right? The word atomically here means nothing can interrupt it, right? This action happens without anything preempting it or stopping it. That's what we use atomic for. So when you do like an atomic addition or an atomic like operation, that operation completes without being interrupted essentially. Cool. We're going to use this compare and swap thing to implement a leadership election on top of a key value store, a distributed key value store. The distributed key value store that the author mentions to use is etcd. So etcd is just a distributed key value store in lock server that was made by the folks over at CoreOS. CoreOS has a pretty cool history if you want to like look them up. They're pretty big with like the container boom. I don't know where they are today. I think they got folded into like Fedora or whatever. But you should look up their history because they were pretty wild for a while.
I've got a question.
Yeah.
Sorry, about the distributed key value stores. It didn't really discuss like what they were, but I'm assuming they're just, it's like a regular hash map, but you have the data across multiple servers, so you have to like send it over the network, I guess. Is
exactly.
That all that it's referring to? That's like a data structure.
Yep. It's basically just a hash map across many nodes. And again, it itself is a distributed system, so it itself has to use all of these concepts we've been talking about, right? So just keep that in mind. Like, just because we're using it doesn't mean that like it doesn't also use some of the patterns in this book, right? It also does. But we're gonna like just call it what it is and say, hey, you're a distributed key value store? Great. We're gonna use you to do a leadership election. So
right.
Layers. It's always layers. It just always comes back to layers, as you've seen.
Containers all the way down.
It really is. It really is. Cool. So the author, if you wanted to follow the hands-on, I didn't follow the hands-on, but the author says if you wanted to follow hands-on, you'd use Helm and the etcd operator. Helm is just a package manager for Kubernetes. All of those YAML files that we've been like playing with or reading in this book, you can just put them all in kind of a directory and package it. I'm using air quotes here as like package it as a Helm chart. So that way anyone that uses Helm can say like, Helm install Matthew, foo, and you would get my Helm chart for my foo service or whatever. And inside that Helm chart can be like a pod or a service or a config map. All of those Kubernetes resources will be packaged up into that and given to you as a Helm package. That's all Helm is. Similar if you're on like Linux, or like if you're on Ubuntu Linux and you do like app install, whatever, similar to that. Or if you're on Mac and you use brew, brew install, whatever. Cool. And then the operators for Kubernetes. An operator is just a way to have like a program that's running on your Kubernetes cluster that responds to certain Kubernetes API requests. That's really all it is. And I was funny reading this little like aside here. He's like, operators are an interesting topic that are being explored. Clearly they wrote this before operators got popular, because operators are like super popular now. So it's funny that like, the author's like, hey, this is going to be like, these are going one way. They're still a new idea. And now they're like a mainstream thing in Kubernetes. So anyway, that's just besides the point. So the author, basically what he does in this hands-on is just deploys the etcd distributed key value store. That's all he does. And once he has that stored, he starts talking about like, okay, now that you have a distributed key value store, how can you actually use it to do a locking so that your leader can hold the lock, and while the leader holds the lock, it's the leader. The author says that we're basically building upon a fundamental programming concept called a mutex. I don't know if you've heard mutex before, but that's just called a mutual exclusion lock. And all it is a way for a like thread in a program to lock and not let other threads like execute as long as they don't have that lock. We're taking that now and we're doing it at the node level. I'm not really going to go into the code so much. If you have questions about the code, we can talk about it. But basically what the author is saying is that like you can implement, and this is all Go code, right? The author's writing Go here. If you were wondering what language it was, it's Go. He's basically saying like we can implement, now that we have a distributed key value store, we can implement a locking logic that we can use for our leadership election using programs like this. And this is what the logic would do. Basically, you just write a function that will return true or false whether or not the lock was claimed. That's it. And then when you do that, though, you can like call a lock. You can create like a new lock function that while the like simple lock is not claimed, you just keep trying, right? So you could imagine us three, if we all start this function and we all call like our lock methods, one of us is going to win the lock and the rest of us are just going to be sleeping and trying to win the lock repeatedly, right? So if I'm the one that held the lock at first, I got the lock. But then if I leave this chat or whatever and like I haven't been seen for a while, you all will get the lock, right? And you might be wondering like, wait a minute, how would it know when to unlock if like a node leaves? Well, it doesn't. You have to build that logic in, and that's where you would take advantage of TTLs, right? Time to live. And you would set a TTL on the lock itself. And while that TTL is not expired, the node that has the lock will remain with the lock. Any questions on that so far? This chapter is a little weird because I know ownership election is not a popular concept, but if you have any questions or anything, feel free to just ask any of them.
I think this is definitely something I would just find the nearest thing that works.
Yep.
From like an existing container or like Kubernetes like pod or whatever, and just be like, yep, I'm gonna use that.
Oh yeah, no, this is a tough one.
Like, yeah, doing this from scratch would be
kind of
I
sucks.
feel like would be very error prone.
Yeah, exactly. And the author even self-admits here. He says we added TTLs to our locks, but we actually introduced a bug. And he basically says that like process 1 can get a lock, it can run really slowly, the lock expires. Process 2 acquires a lock, since process 1 has took too long, right? And the TTL expired. But then process 1 comes back from the dead, finishes, and calls unlock, and it unlocks process two's lock instead. And now process three can acquire the lock. So like we've introduced a bug by adding TTLs, and now we have to add more things to prevent these little edge cases. So the author says we'll add a resource version. So every time we get a lock, we version that lock. And then the author says, okay, we've implemented that, but now we've actually introduced another problem. And we need not just a version lock, but a request version lock. And you can see how this gets really complicated really quickly. So I agree with you. I'd probably reach for something that's off the shelf rather than implementing this myself. But anyway, I kind of already covered this, the ownership aspect of it. So in order, you might be asking yourself like, okay, if you implemented TTLs and all this stuff, how does that like guarantee if I get a lock for 15 minutes and then 15 minutes passes, am I still the lock holder, or like what happens? Well, you can extend this whole idea and come up with a renewable lock, right? So a renewable lock is just a node retrieves a lock, and then every time, every set time period, it tries to renew that lock. And since we read the TCP/IP book, think of it very, very similarly to DHCP leases, right? My DHCP server gives me an IP address. I'm leasing that IP address, right? I'm leasing that ownership, that leader, that master. And every so often I renew my lease to that. I renew my lock, and I maintain my IP address, and I maintain my leadership, right? That's kind of the idea of how this works. And once you do all that, you have yourself a nice little ownership election protocol sort of deal on top of a distributed key value store. And that's all really the author like mentioned in this chapter. He did mention one last little bit. He's like, actually, we're not perfect yet. There's this one little edge case where you can like lose the lock but then come back. And
There's
like
only one more bug.
Yeah,
I
there's only
promise.
one more bug, I swear. So you have to actually do like another check on top of the data in order to do this, and blah blah blah. But I'm not going to go too much into this. Basically, he's saying a leader that is elected and has the lock, it starts making requests to some backend server or whatever. That backend server also has to verify that the service that's talking to it is the one that has the lock, if you really want to like iron out all the bugs. But again, why do all of this, right? Like, why do all of this and have to deal with this yourself? Unless, of course, you have the engineering time and effort to do this. You might want to just reach for something off the shelf.
Yeah. What was the whole point of this pattern again? I think
Yeah, this is a good one.
This sauce.
Yep. This is a tough one because it's not really obvious why you would use this. But the idea is that I think the first chapter kind of, the first paragraph kind of sums it up. Basically, ownership, or this whole leadership election, is finding a node, or like, electing a node that's going to own a task, right? Or many tasks, or a service, or whatever. So in the Kubernetes example, Kubernetes runs as a series of nodes, right? Each of those nodes runs Kubernetes services, like the Kubernetes API, the Kubernetes DNS, blah, blah, blah. You can't just send requests to like any node you want and have it perform the request, because then you can enter yourself into a situation where you send the same request to two different nodes and they both process it and they have a conflict, right? Okay. Somebody has to own the handling of those requests.
So it's not so much like okay, so tell me if the way I'm thinking about this is wrong. I'm not thinking of them as like an owner of the tasks. I'm thinking of them as like a coordinator of like, okay, you go here to this node, to this node, to this node. But isn't that just the what was the last pattern we had that was like a delegator?
The like ambassadors?
Yeah, I think it was ambassador. Is this just like the more general case, or is this applied like at a higher level?
I think you're thinking about it correctly when you say that it owns the coordination. That's a fair way to think about it. Like when we say it owns the task, we don't mean that it owns the execution of the task, but it owns the ability to see that task through, right? Like,
Okay. Yeah.
yeah,
So it does. It coordinates where it goes, and then it deals with like the data whenever the task is done,
correct,
and
correct,
it
correct.
deals with new incoming tasks. And the other nodes are just responsible for like performing smaller subtasks, and then like at the higher level, you just have that coordinator,
Yep.
or master, or whatever they call it.
Yep, exactly. And the reason why this is important is because you want to still have the availability guarantees by having multiple leaders. Sorry, by having multiple nodes, but then one of them being a leader. You know, so that way, in case one of the nodes fails, the leadership control can be relinquished to another node, and the system stays available. Right. But we need the leader to be able to own the tasks, so we don't get like these conflicts and whatnot.
So I guess is it just convenient that any of the nodes can become the coordinator, because like you just have to have less nodes that way, instead of having like say a separate layer that's just like, oh, you have one to like two or three nodes, let's say, so you have like some redundancy that are just like the master nodes, and it's like you pick one of them and then they go down to the next ones. Is it just to like save resources? Because I feel like abstractly that would be easier to handle instead of like passing it between different nodes that have like other functions.
You could. It depends on the system you're working with, right? You could implement this slightly different. There's this whole concept that the author didn't really mention. You can have like multi-master leaders, right? Where you can have like a group of 5 nodes, but then like a couple of them are the masters. Yeah, right. You know what I mean? Like maybe 3 of them
that's
are.
what I was thinking of.
Yeah.
Yeah.
You can have that as
it's
well.
Like normally those other nodes have some other like functionality or like tasks they're responsible for doing stuff. So it's like if it's just those nodes, like you just have 5 nodes and they all have like different things they can do, then you have to like just say, okay, well now you're the master, so they have like, more overhead or whatever.
Exactly. And it depends on the guarantees you want, right? Or it depends on what you want to optimize for as well. I think
yeah, but this name kind of tripped me up. Election. It's more election. They're selecting a whoever is the master. Not like when I first read it, I thought it's like the ML algorithms. You vote to choose one, like elect. This is not technically elect.
Is that where the consensus is the consensus algorithm used to decide which one is the master, or is it like at a lower level to decide like is that all the consensus algorithm is for?
Yes, that's
for
what
deciding which one. Okay, so it's not like a lower level of like deciding. See, I was thinking consensus as something like, I don't know. I haven't read into like machine learning or something, but it's like where you have like a weird set of data and it's like you don't know the exact state of it, but it's like you have like a number or a function that can like get you like an estimate, and it's like you combine those estimates and say, yeah, it's probably that one.
Yeah, exactly.
It's just picking a node. It's not like dealing with the data.
It's just picking a node and maintaining like a node that's picked as nodes like die or whatever, right?
Yeah.
Again, the goal of this is to be highly available. And like I pulled up the HashiCorp Vault documentation because Vault is one of those services that uses Raft under the hood and uses like locks under the hood, right? It uses these concepts under the hood. So you can see like this sentence right here, right? Like to be highly available, one of the Vault servers grabs a lock within the data store. And then that's the active node. And then all other nodes become standby nodes. This is leadership election, right? This is literally leadership that we're reading about right now, right? We literally just read about like grabbing a lock within a distributed key value store. And then that node is the active node and it holds on to the lock continuously. Every other node is just standby, blah, 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 blah. Vault, this particular product, HashiCorp Vault, does additional logic on top of that, and it says like if the standby nodes receive a request, they will forward it to the active node for handling. So in this case, the standby nodes aren't like useless just sitting there. They actually can serve traffic as well, indirectly. So pretty interesting stuff. But again, this all means that they need to you like have some sort of ownership election, right? That's important, especially for a service like HashiCorp Vault, because the whole point of this particular application is to handle secrets, and you definitely don't want secrets getting messed up because like two users try to update the secret at the same time and something happened, right? It then had conflicts. You don't want that. You want to have those requests owned.
So that's
Oh.
okay. So Vault is like a distributed. Like I didn't realize it was distributed. That makes so much more sense.
Yep.
Because I
Yep.
was using it.
Yeah. You should definitely take a look at it. I was looking for a specific article or guide, but I don't remember. But you can take a look at some of these documentations for it. But yeah, that's the whole point, right? The whole point is this is the distributed system. You deploy Vault as a distributed system. So cool. Yeah, I won't go too much into detail about this, but you can look up. There's other ones too, right? You can look up other services as well. Databases are also a big one that are pretty good with distributed systems. You often don't want just one database node. You'll want a cluster of database nodes, and so on and so forth. If you like what is it? Designing data and yeah, this one.
Oh,
This
Don't-
book?
I don't need another book on my list.
No, you don't. But like, if you ever start getting it, like if you get to that point in your career where you're like doing more distributed systems work and you got to think about it under the hood, this is the book. This book is fun, man. I'm going through it right now.
So
as well.
wait, is it for distributed systems in particular?
Yeah.
Like data applications.
Exactly. And they
'Cause I feel
talk
like you
about
can
a lot
have
of this
data
stuff.
intensive applications without a distributed system.
You can, but this is talking about like tens of thousands or millions of requests per second systems, right? Like super scalable ones. But some of the stuff that we're talking about in this book is actually covered in this book in a little bit more depth. So pretty cool. I'm not saying go read it now, but if you ever find yourself like caring about these distributed systems problems in the future, then maybe you might want to reach for this book and like hang out with it, you know? So anyway, sorry, tangents. Cool. And that is ownership election. That's why it's important. That's what it's there for. That's what it is. Any last minute questions on that before we go into the next chapter?
Nope.
Sweet. Okay, we're moving out of part 2. So remember, part 1 was single node patterns. Part 2 was multi-node patterns. And then the part 3 is going to be batch computation patterns, right? Batch computational patterns. Batch as in like a small like subset of work to be done, right? Batch processes, things that like operate on a large data set in small batches. That's what batch processing is in the computing world. And the whole idea of batch processing is allowing you to like do some work over some large data set in small batches. Maybe you're going to like view a bunch of telemetry data and calculate sales or something, right? I don't know, whatever. You're just going to do some number crunching across large data sets. Often when you hear like batch computational workloads, you might be in the business intelligence area, right? Data analyst area. Those are some terms that often come along when you're talking about batch systems like this. You actually have already used batch computational patterns in your programming. I know most of you in here are JavaScript, right? You come from JavaScript. JavaScript has map and reduce, right? It has methods, right? Is it map for JavaScript? It's definitely reduce. But
Yeah.
Okay.
Yeah. It's got an array methods for map and reduce.
Perfect. Yeah. Can you tell that I've been not coding JavaScript lately? But I know it had reduce. I just didn't know it had map. But JavaScript has map and reduce. And you've been doing this in your programs. You've been taking an array and you've been mapping over it, right? So you're operating in batches, usually batches of one, where like each batch is one element in the array. You're doing something to it. And then you're reducing it down to one element or one value. So this is probably the most famous pattern when we talk about batch computational patterns. It's the MapReduce pattern. It's so famous that it's an entire industry. Literally, go look up like MapReduce in the cloud or whatever. Big, there's a lot of companies that have like taken this MapReduce pattern and sold a product around it. Anyway, but the point is that you have a batch computational pattern that you want to do to this data. So let's look at one of the patterns you can use to work in batch processing, and it'll be the work queue. And now I'll be completely honest with you, I don't really like how the author wrote this chapter or how the author presented this chapter. When I was reading this chapter, I was even a little confused as to what the author was trying to get at. So I'm gonna kind of paraphrase it a little bit in words that I think might be better. And if you have questions, I'll be happy to chat about it. But we have a work queue. This is another popular pattern. And basically what happens is you queue up work and something will take things off the queue and start working on them. And what do we mean by a queue? We literally mean the data structure of the queue, right? That's the idea, is work comes in and it goes out. And it comes in using the queue FIFO pattern, first in, first out. A supermarket is the perfect example of a work queue system. Imagine you have one line of customers all trying to check out, and they queue up in a line, and then I guess the self-checkout is probably the best concrete example, right? The self-checkout line in a supermarket, they probably have like 5 to 10 checkout stations there, right? Registers or whatever. And you line up one line. As the stations are ready to process you go to them, right? As a register becomes available, the next person goes, the next person goes, the next person goes. That's this pattern. That's it. That's literally what this pattern is. Work happens, work is queued up, and then as worker nodes are available to do the work, they drain the queue of the work. And they keep doing that again and again and again forever. We could have just literally ended it there, because that's this chapter, right? That's literally this chapter. But any questions on the idea of like a work queue? Okay.
Seems pretty straightforward.
It really is. It's nothing too crazy. The author made sure to tell us a few things though. He says, listen, if you're going to use a work queue, make it generic, because if you make it generic, it can be used across different types of work. If you make the act, and what is he talking about making generic? He's talking about the thing that puts work onto the queue should be generic, and the thing that drains it should be generic. But the actual workers themselves should be application specific. But the author is basically making a case here like, hey, can you please make your work queues generic? That way you can reuse them and stop duplicating code. Whatever. I thought the way he explained it all was a little weird, but that's the idea. And you'll notice he uses the ambassador pattern here to like have something that like drains off the work queue and puts it on. So that's the reusable part here. Again, I don't know why he chose these specific graphics, because I don't think they make a lot of sense. But that's just me. Cool. The author said, go ahead.
No, it was pretty confusing because the first paragraph, it completely explains what it is, but his continuous explanation is a bit cumbersome.
I agree. It's for me, it was weird. So whatever. I guess you have some sort of like body of work, or like data source. You have an ambassador container that queries that data source and then passes it to like the queue, like the work queue manager, which is fine. But I feel like the arrows are almost pointed the wrong way. But whatever. It's okay. I'm not mad about it. Yeah, and then looking at these, see, and even these figures are different.
Yeah, it's like a dependency graph arrow instead of like
Exactly.
the flow of the data, which is weird.
Exactly. But anyway, the idea is that the author says if you're using work queues, please try to make them generic. That way you can agree on an API that your containers or that your applications will implement. And then the thing that puts work onto the queues and the thing that takes work off the queues can be generic because it's just calling out to APIs that have been agreed upon. That's pretty much all he's saying in this part of the chapter. And this is something that I did in my time at HashiCorp. I built a system that did this, literally exactly this. It spun up a queue of work. It had a service that would pull things off of the queue and spin up workers to execute them. I literally built this at my time at HashiCorp. And it's a great pattern, honestly. So outside of that pattern and outside of this like genericness stuff, I did want to call out something that the author states here, and that's like the whole algorithm, like at a high level. He says basically what you're going to do is you're going to have a process load the available work. It's going to see which items were processed or not. For the unprocessed items, it's going to spawn worker jobs. And then once they finish, it'll mark it complete. That's basically what you do, right? Check what work you have to do. Check what work's in progress. Queue up the work that is not in progress. And then as they finish, mark them complete. That's the whole idea. But by doing that, and I'm going to skip the Python stuff because it's not really relevant to us. And I'm going to skip the video thumbnailer because it's not really relevant to us. If you were to do that, though, with a worker, you have to think about how many workers you would have working at a given time. Now, I'm going to go back to the supermarket example because I don't know why the author didn't reach for a supermarket as an example. Like, it would have been perfect if he used it. I'm going to go back to the self-checkout supermarket example. You queue up. Let's say there's 10 registers available. And there's, 10 people line up every minute. And each register can process people in 1 minute, right? That's a perfectly balanced system. As people line up, they get processed, right? The workers can keep up with the incoming work. The registers can check out people, and as people come in, it's flow, right? It's a continuous flow. It's a balanced system. However, let's say school lets out and a bunch of people, like a bunch of students or whatever, come into the grocery store at the same time. That perfectly balanced system will now experience a backlog, right? Or traffic or crowdedness, whatever you want to call it. More people will queue up to use the systems than the system has capacity to catch up with. They'll eventually catch up because, right, those people that school lets out, it's only a periodic spike in load. It's not like a sustained spike, right? There's only so many people that'll come out of school to go into the supermarket. But once that load dies, the system will catch up and everything will be fine. So what the author's trying to say here is think about dynamically scaling the number of workers depending on your load. Having a perfectly balanced system is nice when you have a predictable load on your system. But if the load increases, if it spikes, you might want to consider dynamically scaling up the number of workers that you have to deal with that spike of load, and then you'll scale it back down later when that spike goes away. So in the register example, all those students come in, maybe you open an additional 5 registers. And I know in the self-checkout analogy that doesn't make sense because they only have a finite number of self-checkout registers, but work with me here. So in that example, those students come in, that's a spike of load to your supermarket. Instead of the 10 registers that you have open another 5. That way you can deal with the load quickly. And then once that load is done, you drop it back down to 10. And so on and so forth. And then the reverse is also true. If you have 10 registers open you're wasting resources if your queue only has 1 or 2 items, 1 or 2 people in it, right? Now you're wasting compute time, you're wasting money, you're wasting power. So you also want to scale down when you don't have load. And that's all he was saying in this section. Any question on that? Sorry, I know that I explained that for a while. And I see you typing. Perfectly balanced. Exactly. That's what I was thinking of when I was saying it. But the takeaway there is know your workload, measure the performance, and adjust it. You don't want systems that are sitting there idle all the time, and you don't want systems that are sitting there at 99% utilization all the time. You want a nice balance. So just keep that in mind. My bit rate is higher than the recommended bit rate. I don't care. Take all the bits. Cool. And then the last part of this worker pattern is just extending it to do multiple types of work. So instead of having like a cash, in the register example, it can only do one thing, right? It can only check out a customer, right? It can like scan their items and process their payment. That's it. You can implement a worker queue that can do different types of work, right? So for example, looking at this little graph here, if you have like a work queue, you can have work go on the queue, and then you have some sort of like little middleware layer here that says, oh, depending on the type of work you are, I'll set you to a different worker that can do different things. So if one worker is responsible for, I don't know, renaming an image, and the other worker is responsible for resizing an image, then they have 2 different like jobs. So like the work that comes off the queue can go to the relevant worker. And all the author's saying here is like, don't be afraid to build your pipelines like this, because it'll help you create like single use workers that can be reused easily. And it'll also help you create different sorts of like combinations of pipelines. And I think, yeah, right here, he says, suppose that you have 3 different types of work that you want to perform on a work queue item. For example, you might want to detect faces in an image. You might want to tag those faces, and you might want to blur those faces. These are 3 distinct units of work. If you put all of that work into a single worker, that will be nice, it'll work, but it won't be reusable. Because imagine later on your requirements change and you want to like, I don't know, you want to detect cars. Now you have to change the entire worker. But if you instead use multiple workers and you have workers that are dedicated to single tasks, right? Like 1 worker to detect faces, 1 worker to tag, 1 worker to blur. Well, then now if I change the requirements and say, hey, can you start detecting cars? Well, then you only have to change 1 worker as opposed to like all of the workers inside that 1 worker. That's basically what the author is saying here. And I might not be explaining it the best way, but that's the high level idea. So any questions, comments, concerns? Is this going to be the one stream that I actually do in time? What?
Hold on, I'll think of something. Hold on. There's got to be something.
There's always something.
No, I mean this pattern just makes sense. It's not.
Yeah, they're not too bad. The ownership election one I know is a little weird. It's like, why do I need this at first? And it kind of a little vague, but it's not something, and it's also not something you're probably gonna go like do yourself. You're just gonna use a tool that has this already built in. Yeah. So I totally get it. Trust me, this one always gets me too. It's a tough topic, and the author, and he says it. He's like, this is like he says it somewhere in here that it's probably one of the most like difficult ones. I don't remember where he said it, but whatever. Oh yeah, right here. Distributed ownership is the most complicated and most important part of a reliable distributed system. This is tough stuff. So don't feel bad if you're sitting there like, I don't understand why I need this, or I don't understand what it does. Like, this is stuff that's meant to be like the hyperscalers are doing this, right? Like really, really, really high throughput, highly scalable, highly reliable apps are doing this stuff. And if you're not there yet, that's perfectly fine, right? Cool. Yeah. So any questions about anything? It can, anything from what we read today, what we discussed today. A quick recap. We talked about ownership election. Ownership election is allowing you to identify a leader or a master or an owner in your multi-node system, and that owner owns the task. Sorry, go ahead, Remy.
No, it's okay. My phone was apologizing.
Oh, no worries. Yep. And then that owner owns that task. That way, that task won't be like duplicated, or there won't be conflict, and that task can be seen through correctly through your system. And then we talked about work queue systems. Work queue systems are a pattern under the batch computational patterns, right? So you take a large body of work and you break it up into batches, and you process it in small batches. One way of doing that is with the work queue, where you just queue up work and then you dequeue that work onto worker nodes to be processed. And the example I gave you all was like a supermarket checkout line, right? You have one line that everyone queues up with, and they go to the next available register. That's it. Next week will be our last week. I don't think we're going to read chapter 13. It's because it's only 2 pages, so that'll be up to you, right? It's just this is 2 pages. But next week will be our last week. We'll read chapter 11, which is event-driven batch processing. So we're going to continue the batch, patterns, and then coordinated batch processing. And then we'll be done with this book. And yeah, I hope you all enjoy this book. It's pretty fun one, pretty quick, and it's really just meant to show you the patterns that are out there, right? Like we didn't dive too deep into anything. We just looked at like, hey, what can you do?
Yeah, I can't see myself implementing any of these anytime soon, to be honest.
Oh, that's fair. I mean, and like
it's good to know.
You won't have to, right? Like,
yeah,
until you get there. But now like that these patterns exist, and that you can reach for them. You'll probably do load balancing at some point, though. So that's probably one that you'll probably do.
Yeah, that's probably the more applicable.
I have used these queue things before. Like if you have done any course like distributed operating system, you have this like acquiring lock and the whole. Yeah, I have a question. Do not any of these things in the queue? We don't have any priority queue, right? Just regular one. Like any of this process can be given higher priority.
You can. Yeah, you could if you want to. You can make that worker queue a priority queue if you wanted to. Okay. Right? Like higher priority requests preempt the queue or whatever. You can design it. But often you probably wouldn't design it that way. You probably would implement multiple queues. Right?
Oh.
Like the high priority jobs go to the high priority queue, lower priority jobs go to this different queue, blah blah blah, or some combination, right? You'd have to pick what's best for your system.
That makes sense.
Yeah, because it's like a good example I got asked in an interview, I think, was like notification systems or like 2-factor authentication systems. Those are requests that come in that have to be handled quickly, right? Like if you're logging into your bank account and it asks you for a 2-factor auth token and it sends you one, you would want that sending to happen very quickly, right? You wouldn't want it to be like, oh, I'll send you a 2-factor auth token in 3 days. See you later. Like you would want that to happen fast. So that would be prioritized through your system, right? That'll be something that has to happen quickly versus an email, like a marketing email for like a promotion, that is super low priority, right? So yeah, it's just those are the things you have to think about when you're designing these systems. Like what's the workload look like? And again,
Nice, that makes
there's sorry, yeah. There's no right answer here. It's just dependent on what your work is. So I remember in an interview, I brought up a priority queue for that. And I was like, oh, I'd probably think about what a priority queue looks like here and and chatted about that.
Oh, these chapters are short.
Yeah. These last two
Or
chapters
the
are very
12 is like 2 pages.
Yep. Because they're building on each other.
Yeah.
Because basically chapter 11 is just like,
Oh, it's like
oh, chapter 11 is like, oh, we'll make worker queues that are using events, right? And then chapter 12 is like, we'll do that, but we'll coordinate things. So we'll use kind of a scatter gather approach, right? Like you can see the scatter gather here. So it's just showing you like how they're putting these things together. But and then we're done. We did it.
Yippee. Where's the soundboard?
Oh, I think I turned it off. Yeah, I turned it off. I didn't hear it. I saw the thing.
Yeah, that's a good call, honestly.
Oh, it's because people spammed it, so I just turned it off.
Yeah.
But yeah, no, I know we were talking the other day. I would want to do more book club stuff, probably outside of the Discord, and just keep it more like probably out of this Discord and go to another Discord. I don't know. We'll see, because I do like doing this stuff, and there's a lot of cool stuff to read. And book clubs, I don't know. Book clubs really help me hold on to the knowledge better, because I don't have the discipline to do Anki all the time.
yeah, I love this. So count me in wherever you go, I follow.
Oh yeah, I got you.
And you have my axe.
Yes. No, I love this stuff. I like the book club. I mean,
Yeah.
it's a good way to work through a book and learn some stuff. And even if you're not going to use those things all the time, you've learned some knowledge. I mean, like look at the TCP/IP book. We read that whole thing. Now you all know like what those things are, and when it comes up in your future career and whatever, you'll know how to talk about them.
Yeah, and it's great. Like it forces you to read whatever the chapters you need to read, and
Yep.
also when you discuss with a few people, you get the different ideas. Like something you don't really think somebody else will think. So it's nice. I like discussions.
Agreed. I like it a lot. So I think let me start my new job, and let me let me do that, and then we'll do it the 30th.
Ooh, it's getting close.
I know. I'm excited. I got my machine in. First time I had a MacBook in God knows how long.
Oh wow.
But it's one of the M1 Pros or whatever.
Boo.
Yeah, I know. Boo. These are the blue. I'm not even in the stream because these are the bloopers that everyone needs to hear.
Out the window. Get that.
I will say it's fast. I'll give it that.
Yeah.
But getting used to macOS again.
I mean, hey, as long
weird.
as you didn't pay for it, like that's.
You're not even wrong. You're not.
It's
wrong.
like sure, I'd use a Mac if I don't pay for it. Like I don't.
Exactly.
I just refuse.
I just feel weird because it's like I just want your processor and battery life. I don't care about your operating system. I don't care about any of your apps. I just want your processor and battery life, man. That's it. Like, I just want to use you for the good stuff.
I mean, I don't know. I probably couldn't switch over at this point. I've customized my setup too much, where it would just feel like I couldn't do anything if it was a Mac.
Are you on Windows, Linux?
I'm on Linux.
Ah, nice. Yeah.
So I'd have to like reconfigure everything or do whatever plugins or apps they have to like actually customize like the experience of it.
Yeah. What were you gonna say, Remy?
No, I have all three. I have an old Mac, and I have Windows, and Linux too, because older laptop, I switched to Linux. I play with the I like building stuff like hardware stuff, so it's
Oh,
good to
nice.
have different operating systems.
Agreed.
What hardware stuff do you need a Mac for?
So
Are
Mac,
there any
I
like
still have the Mac. So Linux is mostly I use for
yeah,
the building stuff.
yeah, that makes sense.
Yeah, usually
have an
Linux is what
Windows.
you're gonna use.
Yeah.
I'm finding fewer and fewer reasons to use Windows. Like
Yes.
I just
Embrace
don't.
the penguin.
Yeah.
Embrace the penguin.
I'm at the point now where I'm like, okay, I think I should just re-image my desktop and go straight Linux on it because I don't
Yeah.
use Windows for anything.
I mean, once I stopped playing video games for the most part, I just like, okay, I don't need Windows anymore. Like I'm just gonna switch. Like
That's
there's
kind of
no
where
point.
I'm at. Like
And-
I
and
love
nowadays-
gaming, but I'm done.
Well,
man.
nowadays
I
you can
can't.
even play most games on Linux now because like since the Steam Deck and like Proton, like you can play most games. Like most games will run fine. Like you
But
will
also,
probably have some
yeah.
issues with new releases or something, but like every game I've tried to play in the last couple of years, it's like yeah, it's fine on Proton.
Yeah, I get it. I don't know. I just go ahead.
That's the only reason people keep Windows, like just gaming.
It's
rest-
one of the big reasons.
Yeah, otherwise I don't see the point. Like,
There's
most of
some
the things it's-
software like that's Windows only that you might want to
Yeah,
keep
yeah.
around, but that's less and less the case nowadays. So
Like yeah, getting OBS working on Windows is very easy, right? Like
Mhm.
because all the drivers are there, like GPU hardware acceleration's there, like all the audio stuff's there. Doing it on Linux would be a
Yeah.
pain, but you know what? It's
Yes.
not that bad. Like I don't do anything super advanced anyway, and I do want to get a hardware like mixer and like do all the EQ and stuff in in hardware and like just move everything away from software anyway. So in that case, it would just be like an input output on Linux. So it would be worth, So we'll see. I find myself turning on this Windows machine and then like never, like it's just so bloated with a bunch of crap that I'm never going to
Yes.
use in my life.
yeah,
But
Yeah. Sometimes you cannot even get rid of. I mean, I try to trim. It's like there's no
Yeah.
trimming.
oh, and they have like two
It-
two settings menus, two volume menus, two like what are you doing?
I don't like when Windows 10 switched over to like the new like settings, and it's like they split things between the old like traditional settings menus and then put some stuff in like the new ones. Like I was out. Like it was like I hate this.
I don't blame you.
Uh,
You know what they did? You know when they lost me? When they did this. Yeah, I'll put it on my screen. Whoever did this, these two little
Whoa, what?
icons, these icons.
what
here,
is that?
Yeah,
Is this Windows 11?
yeah.
Okay.
This? Whoever did this, whoever thought this was a good idea, this right here, you killed me. You murdered me when you did this.
What
right
even
here.
is the right one? What does the right one do?
This one's rename and this one's copy.
Oh my
Okay,
god.
I recognize the copy symbol, but
Yeah.
the right one, what? Like,
But then but you have these symbols up here, but then you have symbols and text in the menu. Like what? I don't know. Whatever. You know what? It's okay. I don't want to be mad. I like my life. I like being happy.
don't worry about it.
All right. Anyway, any last minute questions, comments? I'll end the stream. That way people can be like, what the hell these people do?
How is your dog doing?
She's good. She threw up like 10 times last night. I'm not even like exaggerating. I counted. It was about 10 times.
That's right.
Plus or
I think
minus
she
like one or
just
two.
ate something bad or something.
I think so.
probably.
I think she ate something. First she threw up all her, the first 4 throw ups were just food related.
Mhm.
And then after that was just like water related.
Yeah.
So I think she's good now. It's just probably ate something bad. But my wife insisted that I take her to the vet, so I did.
Yeah, probably a good call.
Yeah, I'm gonna go
Yeah,
give her
that's
her pill now. The doctor gave me some antibiotics for her just in case she happened to ingest something bad. But
Makes sense.
Yeah, thanks for asking. Well, cool. I'll see you all on Thursday again for the last book club, and then we'll
Yep,
talk
yep.
about what we want to do after that.
Cool.
Sweet. Thank you all for
See ya then.
joining, and I will see you all on Thursday.
Thank you so
Adios.
much and have a good night.
Thank you. Take care.
Bye.
Bye.